Welcome to Basics of Finite Element Analysis Part 2. This is the 7th week of this course, and what we will be discussing today as well as tomorrow is how do we go around doing numerical integration for problems which are two dimensional in nature. So, we had discussed this concept for one dimensional situations, and we will extend the same thinking to two dimensional problems. But before we do start discussing the two dimensional context, very quickly we will recap what we did for one dimensional systems. So, our theme is going to be numerical integration. And when we were doing the numerical integration in one dimensional situation, then the first thing which we had done was that if we had any element, so it is in x coordinate and the coordinates of the nodes are x1 to x2. So, this is a two noded element, but the same thinking we had applied for quadratic and cubic elements. Then we had mapped this element to another element, and here the coordinate was not x, but it was zeta, right. And what were the dimensions of the element? This was +1 to -1. So, we had mapped this element to zeta coordinate system, and then we did numerical integration in the zeta coordinate system using Gaussian quadrature. So, the first thing we did was mapping, and then we did the numerical integration using, actually we had discussed two methods. One was Gaussian quadrature, using Gaussian quadrature. Okay. The reason we have to map this we said that we have to map it in the zeta domain is because Gaussian quadrature works, the numerical integration scheme of Gaussian quadrature works in zeta domain, where the size of the element is -1 to 1. So, that is why we have to map it. Now, when we did this mapping, what did we do? We had written expressions something like this, that x, so in the x domain the coordinate is x. When I am mapping it, it is nothing but a function of zeta, and this is equal to xi psi I hat, which is a function of zeta, I is equal to 1 to m. And here xi is the ith node of, so I will also put a superscript e. So, it is the ith node of eth element. So, if it is a linear element, then it will have two nodes. If it is a quadratic element, then the node will have on each element 3 nodes, and so on and so forth. And psi I hat is the shape function associated with ith node. Okay, it is the shape function associated with ith node, and please note that psi I hat. So, this is the shape function associated with ith node, which helps us map from x domain to zeta domain. This is not same as psi, because these psi's were what? These are approximation functions which are used to approximate u or v or w, right. So, this helps us approximate the primary variable, but this hat psi I hat, it helps us map from x domain to zeta domain. So, that is why we have put a hat here to mark the distinction. And then the last parameter in this is m, and what is m? M is m minus 1 corresponds to degree of interpolation function, or in this case, because it helps us map the shape of the element, so I can also call it shape degree of shape function. So, m minus 1. So, for a linear element m is 2, because there will be 2 shape functions, and m minus 1 is tells us that the degree of polynomial for each shape function will be 1. It will be a linear element. If there are 3 nodes, then the degree of interpolation function or shape function in this case will be 2, and so on and so forth. Okay. Now, again we have put m minus 1 for u's, right, we had n, because we had also approximated u at element level, and that we had written as u e j psi j x j is equal to 1 to n, right. So, this is an approximation. Here psi j is the approximation function for u, here psi I hat is the shape function which helps us map between x and zeta domains. So, it is important to understand this, and here n is what? N minus 1 represents degree of interpolation function for u. So, there is a distinction here. It is important to remember this distinction. And finally, we had said that dx by d zeta, dx by d zeta is what? We had given it a name, if you remember, and we said that it is a Jacobian of transformation. It is a Jacobian of transformation. Okay. So, this entire thing was for 1D elements. Now, we will extend this thinking to 2D elements. So, for 2D elements, if I have any element so it could be a quadrilateral, and this is in xy coordinate system. If I have to do numerical integration, because I do a lot of FEM using computers, so I have to use numerical approaches. If I have to do numerical integration, and then I have to map this into, because and when I do numerical integration, I use Gaussian quadrature method of integration, then I have to integrate it in the zeta eta domain, and here the size of the element is 2 by 2. So, this is my 0 0, this is 1 1, this is minus 1 1, okay. And let us look at the node numbers. So, these are all local node numbers 2, 3, 4, and in the zeta domain this is node 1, node 2, node 3, node 4. So, this is the mapping. Now, here the mapping is for a 4 noded linear quadrilateral, okay. And the coordinates of this 4 noded quadrilateral are x1 y1, x2 y2, x3 y3, x4 y4. So, node 1 in this original actual coordinate system gets mapped to -1 -1 in this zeta eta domain, and so on and so forth. So, any quadrilateral I can map into a standard square element in the zeta and eta domain, and what is the relation we will see that in a while, but this is for a 4 noded quadrilateral. For a 8 noded quadrilateral, suppose this is an element and I am having the edges may be curved. There is no rule which says that edges cannot be curved. Actually, I will change this. Something like this. So, here 1, 2, 3, 4, 5, oh I missed one node here, 6, 7, 8, okay. 6, 7, 8. So, again here it is in the x coordinate system, it gets mapped into the zeta and eta domain again as a and there is a 9th node here 9. So, this so 1, 2, 3, 4, 5, 6, 7, 8 and 9, and my coordinate system is still the same. So, here a 8 noded quadrilateral with curved edges, it maps into a rectangular, not rectangular, a square in zeta and eta domain. And if I have triangular elements, so I can have any triangle, then it gets mapped as a right angle triangle so this is 0 0, this is 0 1 and this is 1 0. Okay. And similarly, if I have a triangle with curved edges, I can map it as a quadratic, second order. So, this is 9 noded quadratic quad element. Here this is a 3-noded linear triangle. I can map a 6-noded quadratic triangle into a standard triangle in the zeta neta domain also. If this is 3-noded, but I can also have a 6-noded which is a quadratic triangle. Okay. So this is the master element. These are master elements. And we do numerical integration on master elements. Gaussian integration quadrature is performed on master elements. So what we will do is we will discuss only this transformation in this course. This will give you an idea, but if you want to learn about other transformations, you can refer to the books, and the theory is pretty similar. So we will only cover the transformation of a 4-noded quadrilateral to a 4-noded master element in the zeta neta domain. So what are the transformation relations? So x is a function of these two parameters zeta and eta. So in our 1D we had this as the transformation, x of each element was a function of zeta, and it was this function, right. And extending the same thinking here at element level x, and this is equal to and because in 2 dimension we have 2 coordinates. So we have a relationship not only for x but also for y. So the relation to map y, oh there should not be hat here, is this. Now these psi or shape functions are in what domain? They are in the zeta and eta domain. So these shape functions do not change from one element to other element. The only thing changes from if I change from move from one element to other element is these coordinates, right. So xj and yj are the coordinates in the xy coordinate system for a specific element. So these are specific to each element, and this is hat. So the psi function does not change, because the psi function is always in zeta eta coordinate system with, and the location of this square is at the is standard. So these shape functions do not change when I move from one element to other, but what changes is the coordinates of each element. Okay. So the coordinate transformation relation, it changes from one element to other. So what are these shape functions, and they change, they are standard for any 4-noded quadrilateral. So it is psi 1 equals 1 over 4 1 minus zeta 1 minus eta, psi 2 hat equals 1 over 4 1 plus zeta 1 minus eta, psi 3 hat equals 1 over 4 1 plus zeta 1 minus 1 plus eta, and psi 4 hat is 1 over 4 okay. So these are the standard relations. So if I use this transformation, I can map any 4-noded quadrilateral in a regular real coordinate system to a square element of dimension 2 in zeta neta coordinate system. And then in zeta neta coordinate system I can integrate it using Gaussian quadrature and get my values for different elements of K and F matrices or K matrix and F vector. So, these psi's, these are valid only for 4 noded quad. Okay. So, these psi's are only valid for 4 noded quadrilateral. These are valid only for 4 noded quadrilateral. As we have seen several times earlier, so I will like to restate the value of psi 1 at node 1 is 1 and at node 2, node 3, node 4 will be 0. The value of psi 1 at node 1. So, this is my node 1, this is node 1, 2, 3, 4. So, these psi's have been such crafted that the value of psi 1 is 1 at node 1. Okay. What is the value of zeta and eta at node 1? This is node 1, minus 1 and minus 1. If I put minus 1 and minus 1 here, I get minus 2 times minus 2, no 2 times 2 divided by 4 is 1. At all other nodes, this will work out to be 0. The value of psi 2 will be 1 at node 2 and at all other nodes it will be 0 and so on and so forth. So, it is important to understand this. So, m minus 1 is the order of polynomial of shape function. So, if I have an 8 noded quadratic element or 9 noded quadratic element, then it will get mapped into a 9 noded square, and in that case m will be 3. So, here it will be m, so in that case it will be 9. So, m will go from m1 to, right. So, what is m? So, in case of one dimensional elements, we had said that m minus 1 is the order of polynomial of the shape function. In this case, it is square root of m minus 1. That is the order of polynomial of the shape function. So, as and another similarity here is that in this case, when for 1D situation, when m was greater than n, then what was the formulation? Superparametric. That is, when the degree of shape function was higher than the degree of interpolation function for u, then we said that it is superparametric formulation. When it was same as n, then it was isoparametric formulation, right, and when m was less than n, then it was subparametric formulation. So, the same classification of formulation of FE problems exists here, that we have superparametric, isoparametric and subparametric formulation. So, what we have done till so far is we have developed relations which transform x coordinate into zeta neta coordinate and y also into zeta neta. So, using this coordinate transformation, I can transform a 4 noded quadrilateral into a square element of size 2 in zeta neta coordinate system. But what is our original goal? Our original goal is to do numerical integration, right, to do numerical integration so that we can easily compute the values of Kij and Fi for element matrices. So, let us look at an example. Okay. So, Kij for each element, we have developed earlier this relation several times, we can express it as Axy, some constant, times del psi I over del x, del psi j over del y, or in this case I will still keep it del x plus b of xy del psi I over del x, I am sorry, del y, del psi j over del y plus c xy psi I psi j d omega. So, suppose I have to calculate this integral so that I can assign the values of Kij for a specific element. Then how do I do that? What I do is I have to compute each of these terms in terms of zeta and eta, because then if I reassign these terms in terms of zeta and eta, then I can do the numerical integration using Gaussian quadrature. So, what we will next 5 to 7 minutes we will learn is how does this term and this term, how I can express it in terms of zeta and eta. Then later we will know how to handle these terms and also how to handle these terms. We will individually look at each of these terms and we will change the scope of the problem. So, we know that zeta psi is a function of x and y. Now, what is psi in this case? This is not psi hat. So, it represents the approximation function associated with u. Psi hat represents approximation or shape function associated with this transformation. Psi represents approximation function associated with u. Okay. So, this we can write it as psi I, and x itself is a function of these, and y also is a function of these parameters. So, del psi I over del x. So, suppose I have to compute del psi I over del x, then I can write it as del psi I over times del x. So, here psi is a function of x, but x itself is a function of zeta and eta. So, if I have to differentiate it with respect to x, I differentiate it with respect to zeta with x, and then I differentiate it with respect to eta times x. This is I will actually modify this and I can express this whole expression in a different way. So, I am interested in finding the partial derivative of psi I with respect to x, right. But I know that these relations psi I with respect to zeta and eta, I know these relations, right. What I will do is first I will write an expression, this I can calculate psi I with respect to zeta using these approximation functions. I can very easily calculate these. So, I know this thing, and this I can also write it in terms of x. So, this is psi I over del x times del x over del zeta plus del psi I over del y times del y over del zeta. So, I know what is the value of left side, and on the right side I know some things, I may not know some things, agreed. Similarly, del psi I over del eta equals del psi I over del x times del x over del eta plus del psi I over del y times del y over del eta. Okay. Or I can write this in a matrix form, del psi I over del eta, del psi I over del eta equals a 2 by 2 matrix, and in this 2 by 2 matrix I have del x over del zeta, del y over del zeta, del x over del eta and del y over del zeta times del psi I over del x, del psi I over del y. Okay. In this equation for Kij, I am interested in finding del psi I over del x and del psi I over del y. From these relations for approximation functions, I can calculate this side, left side. This is what I am interested in, right. So, this is what we want to find out. So, if I know this matrix, I already know this left side. If I know this matrix, then I can find out this unknown vector del psi over del x and del psi over del y. How do I find out this matrix? The way I find out this matrix is that these are my transformation equations. So, this is equation 1, this is equation 2, right. So, from equation 1 I can find out del psi I over del zeta, oh I am sorry, del x over del zeta. Why? Because these expressions are given here, this expression is given here, right. So, equation 1 helps us compute this matrix, equation 2 helps us compute the left vector. So, then I can calculate this unknown column, understood. This matrix is called the Jacobian matrix. So, in one dimensional system the Jacobian was a number, in a 2 dimensional system the Jacobian is a matrix, in a 3 dimensional system Jacobian will be still a matrix. There we will have del psi I, del x over del zeta, del x over del y over del zeta and del z over del zeta and so on and so forth. So, the movement from 2D to 3D is still same, we still have to deal with matrices. It is from 1D to 2D, we go from numbers to matrices. Okay. So, if that is the case, so if this is a Jacobian, then I can write del psi I over del x, del psi I over del y equals J inverse del psi I over del zeta, del psi I over del eta. Okay. And a lot of times I also call this J star, so that I do not have to write it several times. So, I compute the partial derivatives of psi I with respect to x and y by first computing the J star vector, which is the inverse of J vector J matrix, and then multiplying this J star matrix with partial derivatives of psi's with respect to zeta and eta, and this side is known. So, I can compute del psi I over del x and del psi I over del y. So, in this way, if I have to compute this Kij, I know that I will be calculating this integral in what? Using which method? Gaussian quadrature method, because I have to do numerical integration. For Gaussian quadrature method, I have to go to a zeta and eta coordinate system, and if I have to do in zeta and eta coordinate system, I have to express these partial derivatives in terms of zeta and eta, and that is how I express them in terms of zeta and eta. Okay. So, we will continue this discussion in the next class, and what we will do in the next class is that we will actually do an example, so that you learn a little bit more about how to do these operations. Thank you very much.